Hello, everybody, and welcome to our next section in our Chapter 3, Part 2 chapter. We're going to be working today on something called related rates. We're splitting this section, which is section 3.9, into two different lessons. So we're going to start with some basic questions today, and then the next lesson will be more complicated formulas and shapes. These questions can cause some people a little bit of anxiety because it's quite a bit of setting up. And if you can't set the question up, you can't solve the question. So there are some shapes that you're going to need to know the areas, surface areas, or volumes of. But of course, you do not need to memorize those. And during your assignment, you can access those equations, no problem. So basically, what we're looking at when we talk about a related rate is we're talking about how fast does one thing change in relation to another thing. So when we were doing implicit differentiation, we were talking about dy dx, which was the change in y with respect to the change in x. Or in other words, how fast does y change as x changes? So if I look at something like a circle, for example, if that circle is growing outwards, the radius is changing, but so is the area of that circle. And the way the area changes is not the same as the way the radius changes. If the radius gets bigger, the area of that circle will get bigger faster. So let's look at a couple questions because these sort of ideas are a little bit easier if you try some questions and a bit easier to wrap your head around. So the first question we're going to do is David pours pancake batter into a frying pan. The batter flows outward in a circular pattern, and the radius is going to increase at a rate of 3 centimeters per second. We want to find the rate at which the area within the circle is increasing after 4 seconds. I like to draw myself a picture for basically every related rate problem. I find it way easier to wrap my head around. So if you're pouring batter into a frying pan, we're talking about a circle, and there's some radius of that pancake batter, and there's also some area of that pancake batter, and the area of that circle would be pi r squared. Now, if the circle grows outwards, the area will change. And so we're being told that the radius is increasing at a rate of 3 centimeters per second. This would be dr dt because it's the rate of change of the radius, dr, over time. So if I were to graph this, the slope of the line would be an r over t value. So if I were to, don't write this down, but let's say I had a graph, I would have radius on one axis, t on another. And so if at time zero, my radius is zero, after 1 second, my radius increased at a rate of 3 centimeters per second. So now my radius would be 3. And after 2 seconds, my radius would have gained another 3 seconds and it would now be 6. And after 3 seconds, my radius would now be 9. And so if I look at a graph of radius versus time, the slope of that line would be 3 over 1, 3 centimeters per 1 second. Okay. Now, what it's asking us to find is the rate at which the area in the circle is increasing after 4 seconds. So if it's asking for the rate at which the area is increasing, it's asking us for dA dt. This is what we don't know. This is what we want to find. We know that this one is 3. So if we take a look at our area formula, we know that area depends on the radius. So there's going to be some sort of relationship between how fast the radius changes and how fast the area changes. But this does not necessarily mean if the radius is changing at 3 centimeters per second that the area is as well. We want to find how fast the area is changing. Okay. So let's maybe write this down. This is the change in radius with respect to time. And this here would be the change in area with respect to time. So if I take a look at the formula that I have for area, we can do implicit differentiation with respect to time to come up with a relationship between dA dt and dr dt. So if I do my implicit differentiation on this formula here, we have the derivative on the left side would be the derivative of a. And if we're going to do our derivatives with respect to time, this would be dA dt. On the right, I would have to bring the 2 down in front, and I would get 2 pi r dr dt, because I'm doing my derivative of this formula with respect to time. If I did it with respect to r, I would have dA dr equals 2 pi r. However, the problem there is that I wasn't told dA dr in the question, and I wasn't asked for dA dr. I was asked for the rate at which the area is increasing, which would be with respect to time. So now we already know some information here. 2 and pi are just numbers. We need to figure out r, but we know dr dt is 3 centimeters per second. Now we can find r because the question told us this was happening after 4 seconds. So after 4 seconds, the radius would be 12 centimeters, because 1 second would be 3 centimeters, 2 seconds, another 3, etc. So this means I actually know r, it's 12 centimeters. And if I multiply all this together, 2 times 12 times 3 gives me 72 pi. I'm going to leave it like this. Usually you want to just leave the pi there. You could multiply it out, but when you check your answers, you might find that it looks like you're wrong. You're not, but it's neater to write it like this. And the units, you can see the units here. We've got 12 centimeters and 3 centimeters per second, which gives us centimeters squared per second. And so this is the dA part here, and this is the dt part here. dA, change in area, centimeters squared, dt over time. So this would be the rate at which the area changes with respect to time. So your first step is you need a relationship between your two variables. Once you do the implicit differentiation, you'll have a rate of change relationship between the change in one variable compared to the change in another, and that will allow you to find your missing piece. So the next one, we've got the area of a square increases at 24 meters squared per minute. This would be our dA dt. And the question is asking us, how fast are the sides of the square increasing? So it wants to know what is, let's call this ds for sides of a square, dt. And it says when the area is 36 meters squared. So again, I find it helpful to draw a picture. You might not need one for this. Got a square, and the side length is some length s. And we know that area is side length squared. So again, if I differentiation, I get dA dt on the left. On the right, I can bring down the 2 and get 2s, and then I would have ds dt if I'm differentiating both sides with respect to time. Now I know dA dt, they told us in the question that's 24. We want to find ds dt, but it seems like we also don't know s here, but we do because we were told the area is 36. So since we know the area is 36, we know S is 6. And then we can plug things in. We know dA dt is 24. S is 6. We've been asked to find ds dt. So we get 24 equals 12 ds dt, or 2 equals ds dt. And our units would be meters per minute. And so if I add units in here, let's just go back and add units in here. I'll show you why that works. So we've got 24 meters squared per minute. This is 6 meters. So when I divide 24 meters squared per minute by 12 meters, I get 2 meters per minute. We're going to try some with volumes now. These were areas. So this one looks a little scarier. When you just look at it, you're like, oh my goodness, that's so much writing. It's not. We're going to break it down. So the first one is saying we've got this medical procedure called a balloon angioplasty, a long tube inserted into a patient's artery that has narrowed because of plaque deposits. This balloon is going to be expanded for a short time to make the passageway for blood wider. For a particular patient, the doctor conducting the procedure decides the best results will be achieved if the balloon's radius increases at a rate of 0.15 millimeters per second. So this is dRdt equals 0.15 millimeters per second. So it's saying determine the rate at which air should be pumped into the balloon. So if air is being pumped into a balloon, that is dV dt. And it says the radius is 1 millimeter. Okay. So for the first one, it's saying the balloon is spherical. Okay. So if you take a look back on your first page, we've got if the balloon is a sphere, this one here, this one was a circle. The volume of a sphere is 4/3 pi r cubed. So I want to know dV dt. So if I differentiate both sides of this equation with respect to t, we've got dV dt equals, bring down the 3, and we end up with 12/3 pi r squared dr dt, or 4 pi r squared dr dt, because the 12 and the 3 can simplify to be 4. Most of you will just go straight to that final answer there. Now we were asked to find dV dt. We don't know this, but 4 and pi are just numbers. R, we were told, is 1 millimeter, and dr dt is 0.15 millimeters per second. So this gives us a total of 0.6 pi millimeters cubed per second. And it's millimeters cubed because this in here is millimeters squared, since it's r squared. Okay. So part B is a separate question. Basically, they're just changing the shape of the balloon. They're saying now the balloon is a cylinder with length 1 centimeter. So for B, we still have dr dt is equal to 0.15 millimeters per second. We still know r is 1 millimeter, but now we have a new piece of information, which is your length is 1 centimeter. And again, if we go back to the front page, we see that for our cylinder, we have a volume of pi r squared h. Now, they didn't give us h, they gave us L. And one problem we have before we start and before we start plugging things in is that we don't have the same units here. We've got R in millimeters and dRdt in millimeters, but our L or our H is in centimeters. So this is our H in our formula, but now our problem is that we don't have the same unit. So I'm going to change this to be 10 millimeters. Okay. And now we can find our implicit derivative with respect to time. We're going to need product rule here because we have both R and H. So if I do the derivative of R first, I get 2 pi R dr dt times H plus, using product rule, pi R squared times the derivative of H, which is dH dt. Now we know R, r dt, and H. What about dH dt? Well, the question is, what is dH dt? Well, the question does not say the height of this cylinder is changing. If I think about what a cylinder looks like, right, we can have the radius changing, and that's going to change the volume, but the height does not necessarily need to change. And we were not told the height is changing here. It's telling us a fixed length or fixed height of our cylinder. So dH dt in this question is 0. So we have 2 pi, r is 1, dr dt is 0.15, h is 10 millimeters, plus I times 1 squared times 0. So this entire second term is equal to 0 because the h dt is 0. And now we can calculate what this is equal to. We get 3 pi, and this would be millimeters cubed per second, and this is our dV dt. Again, if we take a look at our units, we've got R here, this is millimeters, dr dt is millimeters per second, and H is also in millimeters now. So you get millimeters cubed per second. Okay. So again, step 1, figure out a relationship between the variables we're given. So in our case, it was a relationship between V and R, or V and R and H. Okay. Then you can do your implicit derivative with respect to time. So when we're talking about these related rates problems, we're talking about as time goes on, these things are changing, and we can write an equation that is then an implicit derivative that relates the rate of one variable to the rate of another variable. So this one is starting with more simple questions, and we will look at more difficult questions in the next section, where it's a little bit harder to maybe draw the picture or to picture what's happening with our situation. And so start with these basic ones first and try more difficult ones next time.